We are discussing operations related to genetic algorithm. Today we will discuss few more operations. So, this is related to reproduction task. The operations are mutation, inversion. So, like the crossover operations that we have discussed, and it depends on the different type of encoding scheme. That means, different crossover techniques are to be followed to different type of GA. So, here also the mutation operations are dependent on the type of encoding scheme that we are following. So, first let us discuss about why the mutation operation is required, or in what context the mutation operation in genetic algorithm is significant. So, basically sometimes whenever the GA is in at an intermediate stage of iteration, it appears that there is not so much desirable level of population diversity. As a result, whatever the solutions are obtained, they leads to a solution, final solution, because there will be no scope of further improvement. Now, in order to search bit in a different direction, so what exactly the thing it is required is that we have to change some chromosomes, some solution in an abrupt manner. So, the way it can be solved, I mean it can be changed, and this is called the mutation operation. Now, the mutation operation is very much similar to the biological mutation, and we know in case of biological mutation, so there is a all of a sudden changes in the gene. For example, in your garden, if you plant a rose tree, and then the flower of the rose tree is, say it is red, then one day all of a sudden it is quite possible that one flower which appears is basically white color, or there is a tree out of so many red rose tree, there is a one tree which produces the white flower. So, this is an example of mutation in our nature. So, similar mutation is followed in case of genetic algorithm also. So, basically it is the idea about that how forcefully we can modify a chromosome. Now, why this this mutation operation is required, we can understand these things if we look at the figure. So, this figure is basically planned for this purpose. Now, we are searching for a solution, and suppose at any instant the solution that we are here. So, if we do some what is called a reproduction by means of crossover and everything. So, from these two solutions it produce another solution here. So, all the solutions are confined into this one, then after some iterations, if we do not find any improvement, then we can accept this solution as the optimum solution. In fact, this is the solution that we obtain is called the local optimum. This is because we can diversify the search space from this region to some other region here or some other region here, so that we can find if some other what is called the optima is possible. So, if we can change some chromosomes from this region to this region, then we can come to this another optimum, maybe the better optimum or the global optimum. So, how these sudden changes in the chromosome can be takes place? For example, if we consider this is the one chromosome, and if we mutate it, then the mutated chromosome this one, it can lead to to your search to some other optimum value. So, this way the mutation operation is very much effective, and it is usually applicable when before taking a final decision that whether we will terminate the DA iteration or we have to do something. So, in that case we can forcefully call the mutation operations on some chromosomes and see whether the mutated chromosomes, solution with mutated chromosome, it can gives better solution or not. So, this is the one way that the population diversity can be achieved, and the mutation operation is meant for this purpose. So, this is the rationale behind the mutation operation, and there are different operations related to the different GAs, and in this lecture we will learn two different GA type, mainly the binary coded and real coded GA. The other two mutation operation in other two GAs like ordered GA and TGA is left as a self study. So, it will not be possible to cover because of the timing constraint. So, we will discuss about two GA, those are basically more important. People usually follow binary coded GA or real coded GA. So, we will discuss our idea about these two. So, in case of binary coded GA, so for the mutation operations are concerned, there are three different versions. One is called flipping, interchanging and reversing. Similarly, for the real coded GA, the mutation operation, two different techniques are followed. One is random mutation and then polynomial mutation. So, first let us discuss about the binary coded GA mutation, and we will discuss the flipping operation first. Now, before going to take discussion about the flipping operation or other GA operations, mutation operation in binary coded GA, we will tell exactly what is the basic concept that is followed so far the mutation is concerned. Now, the mutation operator basically we know in case of binary coded GA, chromosome is represented in terms of zeros and ones. So, if we change some ones into 0 and vice versa, then it is called the mutation. So, basically changing some ones or zeros to zeros or ones, and it is the mutation. Now, the question is that which bits in the binary chromosome should be changes. So, to decide it, so we are to follow the mutation probability. That means, for each bit position we have to decide the mutation probability, and then based on this mutation probability we basically decide that how many bits are to be flipped or how many bits are to be reversed or interchanged. So, this is the one parameter that user has to decide the mutation probability. So, we denote this mutation probability by the symbol mu rho, and there is a heuristic. Heuristic is that this mutation rho should be a very low value. If we take the high value, then your search will be in a random direction, that is sometimes not desirable, and then it will take longer time to terminate the searching process, and you may not get the optimal solution at all. So, there is a good heuristic that is usually followed in genetic algorithm, is that if L is the length of the chromosome, then this mu rho should be within the range 0.1 by L to 1.0 L. So, if the value of L is large, as you see, this probability will also reduce into a smaller value like. Anyway, so this is the heuristic that is followed, and this is the heuristic that is followed to decide the mu rho. It is called the mutation probability. So, like different parameters, mutation probability is also another parameter. It is called the GA parameter to be decided by the user during the execution of the genetic algorithm. Now, having this is the concept mutation probability, we will discuss about the first operations related to the mutation in case of binary coded GA. The operation is called the flipping, and as the name implies, flipping means the 1 will be flipped to 0 or 0 will be flipped to 1, it is kind this. Now, first I told you the mu rho needs to be decided. So, in fact, we will toss a coin and we will decide the coin in such a way that mu rho number of tosses will be 1 and other will be 0. So, somehow this toss can be planned or some program can be written. So, for example, this is the toss. So, this toss is decided in such a way that only few of the bits to be flipped. Now, the bits which are to be flipped, it is marked as a yellow color. So, these bits and these bits. So, if it is like this, then suppose this is the one chromosome that is given to you, we can say the child chromosome or offspring chromosome, and so based on this mutation probability we can flip. For example, it is 1, so this blip will be flopped, so it is 0. Now, all the 0, 0 and 0, so this will remain unchanged. So, this is remain unchanged. Now, again 1, so this 0 will be flipped to 1, and there is a 0. So, this means they will not be changed, and here this is 1. So, it is 0. So, this will be 1. So, this way this is the mutated chromosome can be obtained after the operation of flipping. So, idea is pretty straightforward and simple in fact, and it is also not so time consuming operations, and in generally the child chromosome we have to select at random, that means which chromosome needs to be mutated. So, you can take the child chromosome at random, and not all the child chromosome to be mutated. There are again few child chromosome to be mutated. So, that is also very lesser number of things to be mutated, and it depends on, if you want to have a very high diversity, then you can go for a large number of child chromosomes, and for a smaller diversity it is less number of child chromosome can be considered for the mutation. So, this is the flipping operations, and I will discuss about the next operations, mutation operations. It is called the interchanging. So, in this case again 2 bit position are to be selected at random. So, randomly we select 2 bit position. For example, this is the child chromosome, and then these are the 2 bits are selected at random in between the entire chromosomes there, and then interchanging means this bit 0, if it is 0 it will be interchanged to 1, and if it is 1 this will be 0. It is just like a flipping of course, but in case of flipping operation there are certain tossing required, but here we do not have to do any tossing, only the thing is that we have to select 2 bit position random. Sometimes instead of 2 bit positions we can take 3 bit positions or more number of bit positions, and then accordingly all those bit positions can be mutated. So, it is almost similar as the flipping operation also, but a little bit different way. So, user can try with first 2 bits to be mutated, then 3 bits, and then less number of bits whatever it is there, and this one. So, it is more controllable than the previous one in fact. So, this is the interchanging, and the next operation is called the reversing. So, idea it is basically the idea it is that here okay, in the previous interchanging operations what we have to do is we have to select k number of bits position, but here you do not have to select k number of bit positions. This is basically the mutation operation is required whenever you need a very slight modification in the chromosomes. So, it is basically the idea it is that you have to first generate a random number, okay, or we can say the decide a bit position at random. For example, this is the child chromosome and we decide one bit position at random, this one. Then what is the procedure here is that either the previous bit or next bit whatever it is there. So, we can flip it. So, the previous bit, for example, the next bit, suppose if we consider the next bit 0 1 up to the selected bit, we will flip it. So, if we flip it, then it will give this one 1. So, this is the mechanism that is followed here in case of reversing, and this is again most simple method compared to the previous 2 methods that we have discussed. So, these are the 3 methods that is followed in case of binary coded GA and for the mutation operation. Now, we will discuss about the real coded GA. As I told you, there are 2 techniques, the random mutation and polynomial mutation. Now, let us discuss the 2 techniques one by one. So, first we will discuss about random mutation. So, here mutated solution is obtained by means of some what is called the formula. This formula is basically given empirically. The formula takes the form which is shown here. Okay, so, this is the formula. So, it basically the parent values of the original scheme, it is basically child chromosome, and then it computes some calculation like this. Here the R is basically the random number in the range between 0 0 and 1.0, and delta is also another constant, it is decided by the user. So, this constant it is basically called the perturbation factor. So, if we compute this equation, then it will produce a mutated chromosome that is denoted as P mutated. So, in this operation the task that is required, you have to generate a random number first, and then delta is already predefined constant decided by the user, and use this calculation. This calculation is also simple calculation only in terms of some division, addition and multiplication, not so costly calculation here, and then we will be able to obtain the another value from a given value. So, idea it is like this. Let us illustrate the concept of this random mutation with an example. So, suppose this is the parent value, chromosome value of a child chromosome, and this is the random number which is generated at that instant, and this is the factor that is decided for this process. Then the mutated chromosome can be represented which can obtain this value if we follow the expression which is already stated there. So, this way from one value, that is for the chromosome value belongs to a particular child, will be mutated to another value. So, there is a slight changes basically we have. Now, obviously, how much deflection, how much diversity you want, that depends on this factor. So, we can control these values and then accordingly some values can be obtained which is higher than the value that is required. Okay. So, these are the basically perturbation factor. If we control this value, then the different chromosome, mutated chromosome can be obtained. So, this is the idea about that random mutation. Now, we will discuss about a little bit computationally expensive, but gives better result usually. It is called the polynomial mutation. Now, in this mutation, like in case of random mutation, we have to follow a random number. So, this is a random number r in the same range as in between 0.0 to 1.0, and then we have to calculate another factor here. It is called the perturbation factor delta, and in fact, in the previous method it is the user's responsibility to decide the delta, but in this case it is an idea it is given that the delta can be calculated more statistically or more probabilistically than, and this calculation is based on some statistical function, distribution function which is there. So, one distribution function is follows there if the random number r is less than 0.5, and another function that is followed here if the number less than this one. So, these are the two expression, given by the developer or the designer itself, and we can consider this as empirical formula, and then so following this formula and based on the values of r, we will be able to delta. So, here we can see in the previous case delta is fixed for any operations, but here the delta is not fixed, rather delta is decided by the r value always. So, here because r is there and r is there, and accordingly this one. So, delta is basically dependent on r. So, delta is not truly a fixed for all mutation operations for any other chromosome. So, it is basically varies from one operation to another operation as r varies. And here in this operation another constant to be decided by the user q, like delta that is there, we have to also decide one constant, and that constant can be based on the designer's experience or user's experience. So, once you know the value of q, and then r can be decided at random, and accordingly delta can be computed, and then we will be able to use this formula here. So, the mutated chromosome that can be obtained using this formula. So, p original and delta, and this is again another perturbation factor that we have followed there in case of random, there also you have to constant it, or sometimes only delta something into this one, or some other in terms of values also can be constant. So, anyway, so we consider a fixed deviation that is allowed. So, this is the delta, and then based on these things the mutated chromosome can be obtained. So, this is the idea about the polynomial mutation in case of GA, real coded GA. Here is an example, and in this example we consider the child chromosome, the value is 15.6, r is decided at random 0.6, q is the 2 standard constant, delta is another constant remain throughout this one, and then we have to calculate p mutated. First we have to calculate delta, in this case r is 0.7. So, the second formula needs to be followed, and this formula gives the value of delta is this one, and once the delta value is known, we will be able to calculate using the same formula and then this one. So, if this is the child chromosome, then the mutated chromosome is like this one. So, this way the mutated chromosome value can be obtained. So, these are the two techniques that is there for the real coded GA. Now, we have discussed many operations, and the GA, regarding the GA cycles, we have discussed about the how to create the population by means of the encoding scheme, and then we have also discussed about how to evaluate the fitness of each solution, and then the selection can be carried out, and then we have to create the mating pool. So, this completes the selection operation, and then comes to the reproduction operation. So, for the reproduction operation, the crossover and mutation that have been discussed in details. Now, there is another operation, it is basically called the inversion. It is part of the mutation operation, it is part of the reproduction task. So, in case of inversion operation is a very drastic one operation, usually occurs very little time in the entire GA cycles. Maybe out of the 100 cycles we have to follow 1 or 2, and that is to not to all chromosomes, for some chromosomes. So, the inversion operation is basically select some chromosomes in the current population at random, say out of 1000 we can select maybe say 20. So, 0.2% like this one or this one. Then out of these selected chromosome in the current population we have to follow inversion before going to either crossover or mutation or cycle basically. So, inversion operation basically it will changes in case of binary coded, it will change basically all zeros to all ones and all ones to all zeros. So, this way a drastic changes can take place. On the other hand, in case of real coded GA, if the value is very low, then we can change this to a very high value. So, low to high value or high to low value is the inversion operation, that is in case of real coded GA. And so, these are the operations that is there. We have discussed all these operations. Now, here we have to discuss about the convergence. That means, how to terminate this cycle or how long we have to continue this searching for the optimum solution. So, in the next few slides we will discuss the convergence operations. So, usually the convergence criteria we have to follow. I have listed few important criteria usually the GA programmer follows. So, the first criteria says that the first criteria is basically if we find a solution which is basically our expected one solution, then we can terminate, because if we know that this is the expected result to be, then we can stop it there, and then what are the solution we got it, design values, design parameters result, we can take it as a solution. So, this is basically whenever you expect the desired result satisfying the objective criteria, then we can stop it there. This is the first criteria that we follow. In the second criteria is basically we can define the maximum number of cycles that we should execute. So, is basically how many cycles that needs to be executed. If we decide, say maybe it is 50, sometime 100, depending on your computation affordability, how much computation time that you can afford, we can decide the fixed number of cycles that needs to be iterated, and based on these things second criteria is followed. Now, another idea is that the budget allocation in the sense that I will allow maximum 3 hours to run one GA algorithm. So, 3 hours. So, in the 3 hours if it is terminated before this thing, it is fine. If it does not, we have to continue the search till the 3 hours is over. So, depending again based on the programmer's time available, so they can fix the budgets, that means computation time budget, or sometimes the memory budget also. So, within this memory we have to solve it, then how many iterations, whatever you want you do it. So, it is whatever the budget it is there, time budget or memory budget, we have to follow it, and then so long time budget permits we can cycle the GA operation. The next is, so another criteria is that fine, sometimes we have to find the best solution in terms of say ranking of the fitness. If we find one highest ranking fitness solution, right, that has reached to a basically after a successful number of iterations. So, after suppose 10 consecutive iterations, we are getting the highest ranking solution all the time. This means that we have already come to a global optima, and then we can stop the search criteria there. So, this is the one criteria. And then manual inspection, it is a little bit tedious and very difficult. If it is very small number of solutions are there, then we can do it. So, is basically check the solutions one by one. If we plot the solution graphically also sometimes it works, and then we can decide whether we should terminate this one. So, in this case you have to run one cycle, check the solution manually, and then decide whether you should continue the iteration or stop it. So, this is obviously not a desirable operations, many programmer do not like it. And another criteria is basically combination of any one or any two or any combinations out of the 5 criteria that we have decided. So, this is obviously at the cost of time, because we have to check lot of things in after every iteration, because whether these are the criteria is satisfied or not. So, this is basically the rule of thumb so far the convergence criteria is concerned, and usually we follow this kind of method. Now, so we have learned about the different operations, in particular operations related to reproduction. Now, there are few issues, and these issues are related to the fine tuning the GA operations. One issue in this case is the fitness scaling, and we will discuss about the fitness scaling, and there are different techniques which are there in the fitness scaling approaches. Now, idea of the fitness scaling obtained from one what is called the situations. The situation can be explained like this one. Suppose at any instant of the searching, so these are the solution it is available. Now, if we check the range of the fitness values of the solutions, so we see that these are the range, that means the lowest fitness value to the highest fitness value, this range. Now, sometime this range matters a lot. So this range in fact signify whether there will be a premature convergence or inaccurate result and everything. Now, let us consider a few situations how this gap between the lowest to highest fitness value matters. That means, if the high gap, how it works, if the gap is narrow, then how it works, or whatever the gaps it is required. So, it is basically two trade offs it is there. If fitness values are too far apart, that means they are having very wide gap, then it will select several copies of the good individuals always, and many other worst individuals may not be selected at all. So, this is the one issues are there. So, this will basically tend to fill the entire population with very similar chromosomes, and eventually it will terminate to a local optimum possibly. On the other hand, if the fitness values are too close to each other, that means the gap is very narrow, then the GA will tend to select one copy of each individual, and conjugately it will not be guided by the small fitness variation, and search scope will be terminated. So, it is basically reduced search scope will be explored. So, both the techniques have, both the situations have their own limitation. So, this means that we should have the fitness values of the individuals in such a way that the gap between the highest to lowest should not be narrow neither, or it should not be the wider again. So, there are some reasonable gap. How this reasonable gap can be ensured we will discuss, and the different techniques are there. So, so basically idea is that from the raw fitness value we are to evaluate the better fitness value, and there are three techniques usually followed. It is basically linear scaling, sigma scaling, and power law scaling. We will quickly cover the three techniques here. The idea of the linear scaling is discussed first. So, here basically these are the raw fitness values of the current population, the n number of solutions are there, and this algorithm linear scaling will produce the scaled fitness value. That means, fitness value should be changed so that the gap between the lowest and highest is reasonable. So, idea it is there. So, in this process we have to calculate the average fitness value using this formula. So, it is basically average of all fitness values, and then it calculates f max and f min. That means that is the highest fitness values and these are lowest fitness values. Once these two values are obtained, then it basically follows the decision how to change it. So, basically in this method linear scaling, it computes A and B, the two value using this formula. Once these two values A and B known, we will be able to obtain the scale fitness value using this formula, and this is the fitness value. It needs to be added into the f dash, where f dash is basically the set of all the scale fitness value, and f dash is initially empty. So, this is the method that is followed there in case of linear scaling, and then there is another idea about this is called the sigma scaling, another technique. In case of sigma scaling, so input and output are the same as the previous one. It calculates the average fitness value, it is there, but the difference between the previous linear scaling and sigma scaling is lies here. So, in this method we have to decide two parameters, the S and the sigma, where the sigma is basically the standard deviation of all the fitness value it is there. So, it is basically standard deviation, and S is the one factor, it is also called the sigma scaling factor, and usually this value is in between 1 and 5. It is a standard procedure that is followed. Value, the lowest value of the S as lowest as small as 1, and then highest value is as 5. So, once these values are known to us, we will be able to calculate FW, one calculation for the entire population. So, FW is calculated based on this formula. Once this FW is known, we can use this FW to calculate the raw fitness, the scale fitness value. So, for each f I in f, that is the given population, we have to calculate the scale fitness value f I dash, which is basically f w minus f I, if f w is greater than f I and it is 0 if this is 0. So, this way the scale fitness value for the entire population can be obtained. So, this concept is followed there in case of sigma scaling, and usually the sigma scaling is followed the linear is followed by the linear scaling, because sometimes linear scaling can result some raw scale fitness value is a negative, which is not acceptable. So, we can follow the sigma scaling after the linear scaling, so that the more refined scale feature fitness value can be obtained. So, this is the idea about the sigma scaling, and the simplest scaling is called the power law scaling. It is very simple idea, it is a naive approach. We can say if f I is the current fitness value, user has to decide a k value. K is usually some constant, even including the real value also 1.5, 1.2, 2.5 or 2, whatever it is there, means how much you have to have a variation. So, there then the fitness scale fitness value can be obtained by means of this exponential calculation, and then this is the idea. So, this is very simple and straightforward method. Sometimes it is you followed there in order to have a very good gap between the lowest and highest value. So, this is the method. So, we have discussed about the different scaling operations and the fitness scaling basically, and so this includes the operation that is there. So far the GA reproduction is concerned, we have learned about the GA reproduction, which includes crossover, then mutation, and then scaling operation, convergence criteria, and we will discuss about the next new topics in the next class. It is basically multi objective optimization. Thank you.